So kind of looking ahead, test is next Tuesday. I guess Tuesday's better than Monday. We'll have Monday to review. Tuesday we'll test. Then we do unit circle stuff. Don't check out on me yet on the unit circle stuff. I need you to be here those days. That last week, you know how things are working. They're sort of optional. If you don't come, then I give you a 0, and the grade book drops to 0, and you're fine. If you do come, then you have a chance to bump your grade. So I don't like that system, but it's the system that the district is going with. And so if you want to take full advantage of that system,
is it going to be a multiple choice?
Then that's up to you. It is a multiple choice. So that's at least maybe some incentive to, hey, well, I'll give it a go and see if I do any better, because it can't hurt you. So you may as well try. Second and fourth, let's see, that's us. We're second. The next period is fourth. Are both on Wednesday. So if you're taking the exam, then we'll review, and it's posted already on Monday and Tuesday. If you're not taking the exam, whether you're at home or here in person, if you're not taking the exam, there really isn't much to do on Monday and Tuesday. I can't tell you not to show up, especially while I'm recording. If you don't show up, I will mark you absent. And what does that mean this year? It means if you don't show up, I'll mark you absent. So that's that last week. So you make the decision. If you're sitting on a, let's flesh it out a little more in detail. If you're sitting on a 97, then I mean, why? Like, why bother? But if you're sitting on an 89 and you're thinking, man, I had that one test that was a 78. If I could just replace that with an 85, I'd be much better. So maybe you're on a border. Maybe you're failing. If you're failing, you definitely need to be here to bump you up. That's not many of you. Another way to think of it is, well, if you got a 93 in here, but you have a 78 in some other class, or an 88, and you're thinking, I should probably focus my efforts elsewhere and try to get that score up, if you feel safe about your score in here. So, I don't know what your individual situation is, but look at your grade in here, look at your grade in other classes, and think, well, where do I want to spend some time? Do I need to spend time in pre-cal to get my 78 up to an 80, or my 89 up to a 90? Or is that the situation in English, and so, you'll just take your 91 in here and be done, and worry about making sure you get English up to an 80 or whatever. So it puts it on you to figure out, where do you stand in here? Where do you stand in your other classes? Where do you want to focus your work? Are you okay here? Are you okay elsewhere? And make a decision that's best for you. If you're curious, you want my input, I'll be happy to look at your grades and we can talk about it. But it kind of puts it on you to figure out, where you stand, and are you okay with where you're at here versus where you're at in other places. Don't bail too soon, though. I need you here through next week.
This is from the Phillies.
There we go. Day 3. Trig ratios. So we've done trig ratios. That was on Monday. That was SOHCAHTOA. The new thing for today is trig ratios on a plane. An XY plane, not like an airplane plane.
Wait, unit 8?
Oh, it's unit 7. My fault. Unit 7, day 3. Trig ratios on a coordinate plane, not an airplane. Three Roman numerals today, about equal in length. So the 6 trig ratios given a point. So Monday we gave you a triangle and had you do the 6 trig ratios. Today we're going to give you a point and do the 6 trig ratios, which may seem a little bit weird. Let's just generically graph the point xy. It won't always be in the first quadrant, but makes the example easy. We'll get out of the first quadrant in a minute. So it's like, how in the world am I supposed to do trig ratios with a point just sort of floating in space? Well, you're going to have to make a triangle out of it. But how you make the triangle is super important, because if you make it wrong, you're going to mess up the rest of the problem. So here's the steps. Step 1, this one's easy. I don't know what else you'd do. Plot the point. Okay. How else would you work a problem with a point in it? The next 2 steps are about making the triangle. Connect the point to the origin. Connect the point to the origin. So we start to make the triangle now. By the way, that makes the hypotenuse. You can kind of see it coming here. That makes the hypotenuse. And then lastly, we'll connect the point to the, I kind of have 2 choices here. One of them is the right choice, one of them is the wrong choice.
You're going to connect it back to the point.
So there's sort of 2 options, the x-axis or the y-axis. Do you remember that when we did angles, we always started from the x-axis and measured that way on Tuesday when we were doing, not reference angles, we'll do that in a minute, when we were doing coterminal angles. We started at the positive x-axis and measured from there. So we'll always connect the point to the x-axis, not the y-axis. It's got to be the x-axis. And again, I don't know how to emphasize that enough. That's like, the other things are obvious. Like, of course you'd plot the point. You got to connect it to the origin to make the hypotenuse. But it's tempting, especially if you draw it up close. You're like, oh, just go to the y-axis. You always have to go to the x-axis.
For when you're connecting it to the x-axis, do you want to do it straight down?
Yes, you should do it straight down. I just noticed mine's not exactly straight down until I put a right triangle there, or a right angle, to indicate that it is in fact straight down. Yeah, that's a great point, because you want a right angle. You don't want to go crazy. So connect it to the x-axis with a right angle. All right, well now let's label this triangle that we made. And remember, we only started with a point, and then we sort of built the triangle from the point, but now we have some things to look at. The angle is always at the origin. That should probably be another highlighted thing. Because if you draw the triangle right, but then put the angle up in that top corner, that's going to switch up who's opposite and who's adjacent, and you're going to mess up everything. So the angle goes at the origin. And let's label some sides with what we know. So this side is, or that height of the triangle is the y-coordinate. This side, it would be the x-coordinate. Right? X is left and right, y is up and down. We call this hypotenuse. It is the hypotenuse, but today we're going to call it r for radius. I know it's like radius. Radius of a triangle, that doesn't even make sense. And I get it, that kind of doesn't make sense. But later we're going to take that hypotenuse and sort of rotate it around so it traces out a circle. And so that's where the name radius comes from. So it's like we're looking at one radius of the full circle. But right now it's a triangle. So I get it, radius of a triangle, that doesn't make sense. I'll grant you that. I think we know this, but radius would be Mr. Pythagoras, a squared plus b squared equals c squared. So if you have x and y, you can figure out r. let's see. You know what? Let's also label these with opposite, adjacent, and hypotenuse. So relative to this angle, and again, this is why it's important to put that angle in the right spot, which of those sides is the opposite side? And which is the adjacent side? And which is the hypotenuse? That's the easy one. Sine, cosine, tangent. I'm not going to list the others here because we know what the others are. We don't memorize them. We just know who the partners are. So, ka, toa. So this is the connection to what we did Monday. The extension from Monday to today is that O and H now kind of have different names. Opposite is the y coordinate. Hypotenuse is r. Adjacent is the x coordinate. Hypotenuse is r. And opposite over adjacent, so that would be y over x. So we have this sort of new set of SOHCAHTOA, but it's very much related to SOHCAHTOA. And so there's a couple ways to handle this. Some people are going to memorize the second set. Sine is y over r, cosine is x over r, tangent's y over x. Other people are going to be like, I don't want to memorize that. I'll just draw the picture and figure it out. And that's fine. That works. Because across from the angle, opposite the angle, will always be the y coordinate. The x-coordinate will always be adjacent to the angle, and of course the radius or hypotenuse will always be that longest side. So if you want to memorize those, that's fine. If you don't want to memorize those, if you just want to think SOHCAHTOA, that's fine too. It'll work. So this is what I meant by, if you understood Monday's lesson, SOHCAHTOA, today's not really that much harder. You know how to plot a point, you know how to connect to an origin and connect to the x-axis. So let's find the 6 trig ratios through the point 3, 4. So our 3 steps are plot the point and then build the triangle. I guess that's 2 steps, as long as we know how to build the triangle the right way. So 3, 4. Doesn't have to be perfect. It'd be nice if it was reasonably to scale. You certainly want to put it in the correct quadrant. So there's the point. Now to build the triangle, we connect it to the origin. And then now the first big mistake place. Which axis am I going to connect it to? X. Always the x-axis. So I'll drop down to the x-axis. And now I've built my triangle. And I see that one side is 3 and one side is 4. The second mistake place is to put the angle in the wrong spot. Where does the angle go? At the origin. The angle always goes at the origin. So I'll put my angle right there. That's not 45. If it's 45, these would be equal to each other. I don't know what that angle is. It's bigger than 45. You could figure out what theta is, because you could say sine of theta is, well, let's do tangent. Tangent of theta is 4/3, and then you could do inverse tangent of 4/3 to figure out the angle. But I don't need to know what the angle is. I just want to find the trig ratios of whatever that angle is. All right, how about the missing side? What's that? 5. Good. Most of you, I hope, did not do a squared plus b squared equals c squared. You recognize that that's one of the special Pythagorean triples is the fancy word for that.
3, 4, 5.
3, 4, 5. A little side note while we're thinking about it, because these are common SAT type things.
6, 8,
6, 8, 10, but that's a multiple of 3, 4, 5, so I'm not going to really count that one. Do you remember what another Pythagorean triple is? 12, 13, and 5. Those are probably the two most common ones. And these are things that you don't have to know, because if you don't know it, you use a squared plus b squared equals c squared. But especially on the SAT, that takes time to do that. If you know them, it goes a little bit quicker and buys you a little time. There are others, but we'll stop there because I don't know that we would ever use anything beyond that. All right, back to our 3, 4, 5 right triangle here. So the 6 trig ratios, that would be sine, cosine, tangent. That's the 3 easy ones. The others aren't that hard, as long as you remember who's partnered with who. Who's the reciprocal partner of sine? Cosecant. Kind of setting this up first before I start answering questions. Who's the reciprocal partner of cosine? Secant. And then cotangent is the reciprocal partner of tangent. Now, for this first one, I'm going to write both sets of definitions again, the SOHCAHTOA way and the XY and R way, although I really don't expect you to write both of them. SOHCAHTOA. Or y over r, x over r, y over x. I'm not even going to write those for the other 3, because to find the other 3, I just flip who their reciprocal buddy is. So I'm not going to write down h over a, r over y. I don't need to do that. Let's label our picture here. So 4 is y, 3 is x, r is 5. If you want to label it in terms of opposite, adjacent, and hypotenuse, that's fine too. So again, you can work this problem as a SOHCAHTOA problem, or you can work it as an XYR problem. Y over R, or O over H, either way, is 4/5. X over R, or A over H, either way, is 3/5. And then y over x, or O over A, either way, is 4/3.
So if it's the same, then why do we need to know the y over r, x over r, and that?
It's a good question. Why, if they're the same, why are we even using y, r, and x? The next example, I think, will answer that question, because things get a little bit tricky with opposite, adjacent, hypotenuse in a minute. You can still use them, you just have to be careful on the next example. All right, for the reciprocals, again, I'm not even going to write O's and H's and R's and Y's. I'm just going to flip the answer. Right? That's how we know cosecant is the flip of sine. So the answer is 5/4. I'm not worried about opposite, adjacent, hypotenuse, x, y, r. I'm just flipping sine. Flipping sine. 5/3 for secant. I don't have to go to the square jar for flipping sine, right? That's fine. Cotangent is the flip, the reciprocal of tangent, so 4/3 becomes 3/4. Again, this is why we know these by who their reciprocal partners are, not by the letters. It's complicated enough. Questions on that one? Okay, so what makes things a little bit trickier is when we get out of the first quadrant. So let's find the 6 trig ratios. Same question for -3, 5. So we plot the point, -3, 5. I guess another less common error is to plot the point in the wrong spot, but I can't help you if you can't find negative 3, 5. Sorry. Let's see, now we need to build a triangle. So connect it to the origin. Connect it to the x-axis. Always, always, always to the x-axis. I've picked both examples to be closer to the y-axis because that's when students are most tempted to be like, it's closer to the y-axis. No, always, always to the x-axis. All right, the x-coordinate was negative 3. The y-coordinate is 5. Okay, this looks a little bit weird because now it looks like I have a triangle that has a side of negative 3. Which doesn't really make sense, but it's still accurate. Where does the angle go?
The origin.
At the origin, but the angle always starts from the positive x-axis. So the angle is really this angle. It's like, wait a minute, that's a little bit weird because that's not even in the triangle. And so this is where SOHCAHTOA starts to break down a little bit. To hurt. But before we do that, let's find the missing side.
Wait, is this the Pythagorean triangle?
Is this another 3, 4, 5 triangle?
Well, it's 3 and 5.
It's 3 and 5.
It's negative 3.
Is it 3, 4, 5 though? Why not? The 5 would have to be on the hypotenuse for it to be a 3, 4, 5. So again, that's why I picked this example, because some people are like, oh, 3 and 5, the missing side's got to be 4. No, 5 has to be the hypotenuse if it's a 3, 4, 5. So r squared is the square root of x squared plus y squared. 9 plus 25 is 34. So I've got a weird side to deal with. That's okay though. We know how to fix these things. Yes, we do. Okay, well now here's where opposite, adjacent, and hypotenuse gets a little bit tricky. Well, hypotenuse isn't tricky, that's obvious. Which side would you say is the opposite? Well, it's one of those, yes. And this is why x, y, and r work a little bit better, because 5 is the y, 5 is also the opposite. The y is always the opposite. But that's opposite the angle. You're like, well, not really. Like, opposite the angle is nothing. But opposite that angle, where the angle is, kind of, maybe. So this is where SOHCAHTOA is a little bit, you got to be careful. It's safer if you did r and x and y. But you can still use SOHCAHTOA as long as you know that the O is opposite the angle. The O is always the y. The A is always the x. Another way to remember that, if you write it as an ordered pair, x comes before y and A comes before O. So they're alphabetical, if that helps. So the 6 trig ratios. And this time I'm not going to write out either one. I know that sine is opposite over hypotenuse, or y over r. So I look at my picture, and if I'm thinking y over r, or o over h, either one, 5 over square root of 34, which needs to be fixed. So 5 root 34 over 34. Cosine is adjacent over hypotenuse, or x over r. Negative 3 over root 34. And I feel like I've done that enough times in my life that I don't need to show the work for that. You can do the same. And then lastly, tangent is opposite over adjacent, y over x. 5 over negative 3, and that doesn't need to be fixed, so we're good. Well, we're good with those three. The three reciprocal partners. Again, I don't think about y's and x's and r's and opposites and adjacents and hypotenuses. I just flip the sign. I got two options here. Do I want to flip the original or flip the fixed? Flip the original, because then I'm done. Same thing with cosine. Flip the original. And the negative can go in the bottom. It looks a little bit weird maybe with a negative in the bottom. It's not wrong, but I'll probably put the negative out front. And then same thing for cotangent. Negative 3/5, nothing to fix there at all. Plot the point, connect it to the origin, connect it to the x-axis, and then be careful. Most of you are probably going to stick with opposite, adjacent, and hypotenuse. And that's fine. Just be careful. Opposite always goes with y. Adjacent always goes with x.
So for Pythagorean triples, has to be the hypotenuse?
Yes, for Pythagorean triples, because the longest side is always the hypotenuse.
Okay, that makes sense.
So yes, and there will be times where we try to trick you with ones like this, because your brain says, oh yeah, 3, 4, 5, and if you slow down to think about it, hopefully you think, wait a minute, that doesn't really work. I can't have 4 as the hypotenuse when one of the legs is 5. But if you're trying to go fast, maybe we get you. All right, let's talk about the signs. Not the SIN, but the SIGNS. Of sine and cosine and tangent.
Is this Roman numeral 2?
This is still Roman numeral 1. This is the tail end of Roman numeral 1. Although Roman numeral 1 is longer than 2 and 3. There's 3, but they get progressively shorter. Let's see. R is always positive. That's maybe an important thing to remember. So I don't have to worry about R being positive or negative.
Is that one of the weird looking R's?
No, it's a regular R.
The one that has the line in the
So let's think about where Y is positive in the quadrants. Certainly in the first quadrant it's positive because everybody's positive. What about in the second quadrant? Is the Y coordinate positive in the second quadrant? Right, Y is how far up or down you go. So if you're up, you're positive. If you're down, you're negative. So what we just found was the sine of sine. That's a weird thing to say. The sine of sine. The SIGN of SIN. Sine is positive when Y is positive. So sine is positive on the up stuff. Cosine is more concerned with where X is. So where is X positive? Yeah, some of you are just pointing, like, yeah, over there, on that side, on the right. So that's the sine of cosine, the SIGN of cosine. Tangent, we have to be a little more careful because Y and X depends on both of them. So in the first quadrant, Y is positive, X is positive, everybody's positive. We're all good.
So that's the way for all of us.
In the second quadrant, Y is positive, but X is negative. So that would be negative. Positive divided by negative. In the third quadrant, Y is negative, X is negative. That's a funny looking thing, but negative divided by negative would be positive.
Looks like you messed with efficiency.
And in the fourth quadrant, let's see, Y is negative. They have opposite signs, so it's negative. Now, some of this, not some, that takes care of itself, but it's helpful to remember as a check at the end of a problem. If you're in the third quadrant, sine is negative, cosine is negative, tangent's positive. If you're in the fourth quadrant, sine's negative, cosine's positive, tangent's negative. But there is a little bit of a shortcut. Again, this takes care of itself. If it doesn't, you can check it figuring this out. And so this little shortcut is sort of doubly unnecessary, but people find it helpful. Who is positive by quadrant? And here's our shortcut. You know how to number the quadrants. You go around 1, 2, 3, 4. So let's come up with an abbreviation. So look at the previous three graphs. Who was positive in the first quadrant? All of them. So let's just put an A there, because they were all positive. Who was positive in the second quadrant? Just sine. Who's positive in the third quadrant? Just the tangent. And who was positive in the fourth quadrant? Only the cosine. So this is not, in fact, a true statement, but it helps us remember all students take calculus. It's a great encouragement as for a pre-calc class, right? All students take calculus. Of course they do. This is not something you have to memorize. This takes care of itself based on the signs of y's and x's. But it's something that a lot of people will take the time to memorize because it's not hard. And then you have sort of a built-in check for this entire test. So what I see on this test and almost all the tests going forward, a lot of times students will write their name on the test and then they'll do that little picture. And everybody knows all students take calculus. They're reminding themselves who's positive in which quadrant. If that's helpful, do it. It's not necessary because it takes care of itself, but it's a really easy thing to remember and a real good check on your answers. All right, Roman numeral 2. Yeah, these definitely get quicker. Reference angles. These become super, for right now it feels like, why are we doing this? I don't see a point of this. They become super important in the days and weeks ahead. So it's one of those foundation lessons where you're like, why? What's the point of this? This seems easy. It's not hard, but what's the point? The point is, I'll tell you later. That's not very fulfilling, I get it. But we're building up to something. The reference angle is the smallest angle to the nearest x-axis. The smallest angle to the nearest x-axis. That's a little bit repetitive. Get to the x-axis as quick as you can, as in a quick a way as you can. And the good news is it's always positive. So you don't have to worry about quadrants. You don't have to worry about which way am I rotating. It's just like, how big is that angle to the nearest x-axis? Some examples to make sure we're on the right track here. So let's find the reference angle for theta equals 27 degrees. We're going to have to back up a second, but 27, what quadrant is 27 located in? The first. Again, when we do it in degrees, everyone's fine because you have a pretty good feel for degrees. So there's 27 degrees. So how close is it? There's not a point really, it's just this full angle that goes forever. What's the angle? And if you're thinking this question is so easy it's dumb, you're right. What's the angle to the nearest x-axis? 27. 27? Maybe? Yeah, the reference angle is 27. When you're in the first quadrant, reference angle is kind of dumb because it's equal to whatever the angle is. Things get a little bit trickier when we're not in the first quadrant. Let's say theta equals 95. Well, what quadrant does that land me in? The second, because 90 is straight up, so 95 is a little bit into the second quadrant. So there's 95. The reference angle, though, is to the nearest x-axis. Well, I don't want to go all the way back to the positive x-axis. It's a lot quicker to go right here. But then I got to figure out what that is. It's 180 minus 95. Also known as 85. So the reference angle is get to the nearest x-axis as quick as possible, the shortest way possible. Let's do one more in degrees, and then we'll switch to radians. Radians is what messes us up sometimes. 253 degrees. Well, what quadrant would that be in? Well, let's see. That's 90. So that's 180. What's this bottom degree marker? 270. 360 would be all the way around. So now I think it's pretty clear that 253 is in the third quadrant, closer to 270 than 180. So I don't know, somewhere right in there. That's probably even closer to 270 than I drew it. That's 253. The reference angle is get to the x-axis as quick as possible. So there's my picture. So what would it be? 73, because it's 253 minus 180 is 73. Now, you can teach it as, let's learn the formula for reference angle based on the 3 different quadrants. It's like, no, then you've got to memorize a whole bunch of different stuff. Memorize or know what the reference angle is. Get to the nearest x-axis, and then you just figure out, well, am I subtracting 180? If I subtract from 180, am I almost at 360? You just kind of figure it out. But I'd rather you figure it out than memorize 4 more formulas to think about. All right, let's do some in radians, because that's what's going to challenge us a little bit. Maybe before we do radians, though, let's label a set of axes in radians. So 0, that's the easy one. Let's see if we can figure this out. If we go all the way around, We know that's 360 in degrees, but what was all the way around in radians? 2 pi. And if that's all you remember, you can figure out the rest. Okay, so you don't have to memorize this. Once you know that 2 pi is all the way around, well, what's halfway around? Pi. Again, you don't have to memorize that pi is equal to 180. You can just know that it's halfway. And then halfway between 0 and pi is half a pi, 1/2 pi, or we usually write pi over 2.
2 over 3 pi.
And then halfway between
3 over 4.
1 and 2, here's where our fraction brain has to really think a little bit. Okay, so that's not wrong. That's not what we write, but it's not wrong. It is 1.5 pi. That's true, but you'll never see a math teacher write that, other than I just wrote it. But after today, we're not going to be writing 1.5 pi. But it's not wrong, and it does illustrate that it's right in between 1 and 2, so that's good.
Pi over 2.
Now, what is that as a fraction? 3 pi over 2. All right, now for the fun stuff. Let's find the reference angle for 13 pi over 12. That's exactly how you should think of it. 1 and 1/12 pi. And if you think of it as 1 and 1/12 pi, I hope it's easy to figure out what quadrant it goes into. If it's 1 and 1/12 pi, which quadrant does that land in? The third. Because pi is the cutoff, but we're bigger than pi, so we're going to go 1 and 1/12 pi. That looks a little bit funny to write it that way, but it's not wrong. And it's actually a great way to write it to figure out what the reference angle is. How much past pi, how far past pi did we go? 1/12 pi. So when you said 1 and 1/12 pi, that was a great way to say it. 1 gets you to that marker. 1/12 past it means our reference angle is pi over 12. This takes some fraction sense, and if your fraction sense is weak, it's going to be exposed here. I don't know how else to say it. 13 pi over 7. 13 over 7. 0, 2 pi, pi.
1 6/7 pi.
1 6/7 pi. Not bad. 1 6/7 pi, though. So it's definitely bigger than 1. We're
It's
past
2. It's almost at the 3/6.
That's a great way to say it. It's almost a 2, right? 14 sevenths would be 2. So we're almost a 2. Almost a 2 is a great way to say that. In fact, speaking of almost a 2, how far from 2 are we? Because that is the reference angle. We're a seventh away from 2. So the reference angle is pi over 7. So reference angles aren't hard if you can think about fractions. If fractions are hard, then reference angles are going to be hard. Let's do one more. Negative 3 pi over 4. Negative 3 pi over 4. What's the negative mean?
It's going to be in the quadrant. I know. It can't be.
Well, first, negative means we go backwards. So we know we're rotating backwards. What's backwards 3/4?
It's going to be in the second quadrant. Okay, when it's split. So the third quadrant.
Yes, it's into the third quadrant. So backwards this way would be negative pi over 2, if you want to relabel the quadrant markers, which is a little bit weird, but not wrong. So it's into the third quadrant. That's backwards 3 pi over 4. And how much farther to get to the x-axis there? A fourth, so pi over 4. So reference angles, as long as you have a a decent fraction sense about you, you'll be fine for the radians. You'll probably be fine for degrees either way. All right, last Roman numeral. I know, longer than usual. I'm on to a second full page of notes, which I usually don't get to. I like these problems because you have to think a little bit. I don't know what to call them other than puzzle problems. And there's nothing new to teach. We're just going to put some things together. So we're just going to do some examples. If tangent equals negative 4/3 and sine of theta is less than 0, then theta is in quadrant. Well, that's the question. So some people can do these completely in their head. Most people want to draw a little bit of a picture and think about all students take calculus. Again, you don't have to draw that. You could think of it in your head and just do the kind of process of elimination. Where is tangent negative? Let's do that first. What quadrants have a negative tangent? Tangent, tells us where tangent's positive. So I can't be there or there. I'm either in second or fourth if tangent is negative. But if sine is negative, let's see, where's sine negative? That would be third or fourth. So this has to be in the fourth quadrant. The fourth quadrant is the only place that has a negative tangent and a negative sine. And I don't know who decided we would number quadrants with Roman numerals.
So that's the answer.
That's the answer. Quadrant 4. If cosine of theta equals negative 3/4 and tangent of theta is negative, then theta is in quadrant. You figure that one out. So example 3, if cotangent of theta is negative 3/4 and the sine of theta is negative, let's find the secant of theta. Well, I need to draw the picture if I want to find secant of theta. Let's see, secant is the flip of cosine. So I know it's h over a or r over x, but I need to have a picture before that's really helpful. Cotangent. I don't want to mess with cotangent. Just flip it. When you say flip it, what could I write that means the same thing as cotangent equals negative 3/4? Yeah, tangent equals negative 4/3. Okay, so I'm done with cotangent now. So if you get one you don't like, flip it, and then you don't have to worry about the reciprocal thing anymore. So I need to draw a picture. Well, first I need to pick the quadrant. So tangent is negative, sine is negative. Tangent is negative, sine is negative. What quadrant is that going to be in? Let's see. Sine is negative in third and fourth. Tangent is negative in second and fourth. So it's got to be in the fourth quadrant. So I'll draw my triangle in the fourth quadrant. Hey, Ray.
So it seems like we do need to memorize like where things are negative. I don't understand how the A, C, S, T, C takes care of that. I thought that only was for positive.
It tells you who's positive there. You're right. So everybody's positive in the first, sine's positive in the second. That means sine is negative in the other two. Cosine's positive in first and fourth, so cosine is negative in the other two. So yes, this specifically tells you who's positive, but by telling you who's positive, it's also telling you who's negative. In the third quadrant, tangent is positive, but the other two are negative. Let's see, tangent is opposite over adjacent, or y over x. That might be more helpful, because I'm going to go backwards now, and I'm going to label the triangle based on this information. So it's kind of a backwards problem. So opposite is 4, adjacent is 3, and that 4 is negative because it's going down. So I'm using that information to draw the triangle. I want secant though. What do I need if I want to find the secant? I need the hypotenuse. What's the hypotenuse? You sure? Yes. This one is a 3, 4, 5. And hypotenuse is never negative, so I don't have to worry about that one. So the secant of the angle is the flipped cosine. So that's ha, or x over r. X is 3, r is 5. So, wait, I wrote that wrong. I wrote h over a right, and then I messed it up from there. R over x, 5 over 3. And that might be why I should stick with SOHCAHTOA rather than r's and x's. Alright, drawing the triangles is probably the hard part, so let's draw another triangle. We won't find the trig ratios. That's the easy part. If cosine of theta equals negative 1/2 and tangent of theta is positive, let's just say draw the triangle. Because I think if you can draw the triangle, you can get the SOHCAHTOA stuff right. So you try that one. What's cosine in terms of opposite adjacent hypotenuse? X over r, or a over h. And so now I know that x is negative 1 and r is 2. And how do I find that missing side? Pythagorean theorem, a squared plus b squared equals c squared. So negative 1 squared plus b squared equals 2 squared. Right, because you got to have c as the hypotenuse. So 4, move the 1 over. So the missing side is length square root of 3. Does anything look not quite right about that? It is the square root of 3, but think about this coordinate right here. It has to be negative. Okay, and the Pythagorean theorem isn't going to tell you that. Only looking at the picture is going to tell you that, wait a minute, if I'm in the third quadrant, that's negative. Another way to do it is when you take the square root, you're supposed to put plus or minus on there and then figure out which one it is. And based on the picture, it's negative. Once you have the picture, then you could answer sine, cosine, tangent, cosecant, secant, cotangent, whatever we ask you to. But building the picture is the hardest part. All right, that was a lot of stuff today. Today's assignment is worksheet 3. That was a lot of stuff. But hey, it's block day. You still have some time left.